So, welcome back to this lecture series on air pollution, fundamentals of air pollution, sources, mitigation and effects. Okay. In this lecture what we are going to discuss about radiative forcing, and as we discussed in the previous lectures, we defined relatively some terms like radiative forcing, we defined greenhouse gases, their global warming potentials, and then lifetime as well as concentrations, and we discussed that how they are actually helped our atmosphere keeping in warm. But then we also discussed, but if the also discussed that if the concentration of these greenhouse gases are higher, they keep on increasing, there will be more trapping of infrared radiation that is emitted from the earth surface, and which means this will be actually going to have a kind of cooling warming in the atmosphere. So, this is the this we will discuss, and in this lecture we are going to discuss further in this one. Lastly, we will introduce about the aerosol cloud interaction, and then we will move to the feedback mechanism. So, radiative forcing, if you see the textbook definition, it is actually net change in the total irradiance, and just remember this means the unit will be watts per meter square at the troposphere, tropopause, or at the top of the atmosphere, sometimes it is written, and to an applied perturbation. This is very important. When we say that applied perturbation, it could be because of, for example, greenhouse gases, you either add or remove, or you add more of aerosols or remove, and then depending on whether you add more of scattering type or you are adding more of absorbing type, this can be changed. Okay. Generally, the net solar irradiance is actually will be a short wave radiation that is coming from the sun, and long wave radiation that is outgoing from the earth. Actually, you take some of this one, and conventionally we calculate down minus up. Okay. So, usually we take that down we take as a positive, and up means we take negative, and conventionally if you calculate this value, if it comes out to be positive, means down was positive, this was negative. So, if the difference is positive, this means down is more. So, this means somewhere this energy is released, or it is there in the atmosphere, it is trapped in the atmosphere. In this case it will be called warming, and if it is a negative, then it will be called as cooling, okay, of the atmosphere. There is another very important parameter called climate sensitivity parameter, and this is defined as for well mixed greenhouse gases, delta Ts is equal to lambda Rf, and lambda is actually climate sensitivity factor. So, based on this one lambda, if you just see here, so lambda will have a unit of Kelvin per watt meter square. Okay. So, something like that it will have lambda. So, per unit how much actually per unit change in radiative forcing, how much change is going to happen in the temperature, that is called climate sensitivity. So, this is what you see here in the top of the atmosphere. You have radiation that is reaching on this one from the radiation that is actually there is nothing in between absorbing or scattering, but what is happening, all the radiation you assume that is coming here. Earth is emitting actually like IR radiation. So, this is there on the top of the atmosphere, some of this one is lost and some of this one is actually added in the system. So, if you increase the CO2, what will happen? Lower atmosphere will warm, because CO2 increase means it is going to trap more of the radiation, and this means this is going to increase the temperature, whereas the stratosphere will be in cooling and it will have actually kind of positive forcing. So, in generally this is the concept of greenhouse gases that we discussed for not only for CO2, you can take this concept for any other greenhouse gases, which actually tells that this will trap more of the IR radiation in the lower atmosphere. So, this means this is warming and it will have a positive radiative forcing or positive forcing. For aerosols, this is in comparison to greenhouse gases, this is little bit more complicated, okay, and it depends on the aerosol properties. For example, I discussed about scattering and absorbing, plus characteristics of the underlying surface, that what kind of surface it is there, whether the surface is reflecting or it is more kind of transparent. So this is actually there. For example, here it is considered that aerosol scattering aerosol over the dark surface. What is happening? This radiation, if you remember in the previous slides, all the radiation was reaching to the earth surface, nothing was reflected, but if you see, because of the presence of the radiation aerosols, part of this will be reflected. So this radiation is now scattered back to the atmosphere. So what will happen here? Okay, you have actually in the top of the atmosphere, there will be a reduced short wave radiation, because part of the radiation is scattered back. So reduced incoming solar radiation at the surface, you have negative, less value, and more short wave radiation is reflected in the space. This means it will have a negative forcing or cooling, and this means local surface and atmospheric cooling. So this is actually the concept for the atmospheric aerosols, that atmospheric aerosols will lead to kind of more cooling in the atmosphere. Similarly, if you consider a case for absorbing aerosols over a bright surface, now what is happening here? Radiation comes here, but this part actually has absorbing aerosol, more absorbing aerosols. So whatever the radiation that is actually emitted from here, it will not be actually transmitted. Part of the radiation will be absorbed by this one. So whatever radiation was there, it will be absorbed. There will be a decrease in the radiation. So this means what is actually happening here, less short wave radiation is reaching at the surface, more is absorbed in the atmosphere, and less is reflected to the space. So more is absorbed in the atmosphere. So like in the greenhouse gases, if more radiation is absorbed, it will have a positive forcing. So it will have a warming effects. So this means, and actually less radiation reaches the surface, and because less radiation reaches at the surface will be having a kind of cooling. So you have actually local surface that is cooling, and atmosphere is warming. This very strange and very kind of disturbing, because the atmosphere that is there, it is already divided in a different kind of so it will have a different impact if you talk about the surface, for example processes, and in the atmospheric processes. So how to calculate radiative forcing? In order to calculate radiative forcing, we need to calculate key aerosol optical properties, and we will discuss in one by one here. The very first one is actually size distribution and chemical composition. So usually if you have a measured chemical composition, then it is okay, or if you don't have a measured one, then usually they take chemical complex refractive index. These are taken actually as a input, and when these are the inputs, they are processed. What they are processed, and then in this one actually it is not very simple. So you have to assume that particle shape. Okay, so particle shape, for example, if you assume that whether it is a spherical, then in that case my theory will be applied. If you assume that this is a kind of a spheroid, not a sphere, then T matrix kind of logarithms has to be applied. So you assume the particle shape, okay, and this is where the measure of this leads to the uncertainty in the calculation of the radiative forcing, because if you rightly assume the particle shape, you are going to get a right combination of the aerosol optical properties, whereas if your assumption about the particle shape is wrong, you are going to get long optical properties, and therefore the radiative forcing calculations. And then appropriately you do it kind of scattering code you apply. You have to consider size and size parameter, for example 2 pi r upon lambda is for the scattering. And what is the output that you get? Output you usually get mass extinction coefficient. Just remember this one, we simply did not put mass, we simply said that it is extinction coefficient, and extinction coefficient you also need absorption coefficient, and you need to know scattering coefficient, and if you know these and you already have calculated this one, you will be able to calculate single scattering albedo, because omega was nothing but B scattering divided by B absorption plus B scat. Okay. So, if you have, for example, calculated this is, and this is nothing but B scattering divided by B extinction. So, B extinction you have calculated, and somehow if you can calculate B scattering as well, you will be able to calculate single scattering albedo. There is another very important parameter that is called scattering phase function, that has to be there, you have to include, and this is kind of peak extinction you have to see, you have to give by number as well as volume. So, both the distribution you have to see that what is the number, what would be the number of the particles, because if you remember the scattering coefficient calculation, number of the particles were very important, and then if you know the right things, and not only that, you have to give them in nucleation mode, Atkin mode, accumulation mode and coarse mode. All the 4 modes you have to give that what is the concentration of the aerosols, and different type of aerosols with their size. So, then it will give you the kind of extinction coefficient, you can calculate scattering albedo, and then you can calculate scattering phase function, you can do this one. There is a very important model that is actually used for radiating, for calculating the estimation of radiative aerosol optical properties. This is usually called OPAC, opaque. Okay, aerosol optical, sometimes it is written differently. Okay. And in this one, the input actually, like we discussed here, the input is actually, this is a very simple model, and here the input is actually you have measured aerosol chemical composition, and this is where I do not do, for example, radiative forcing calculations, but I do measurements of aerosol chemical and optical properties. So, these inputs, if you remember in the previous ones, like single scattering albedo, absorption and scattering coefficient, we can measure, and that we can use to calculate the some of the input parameters. So, you do aerosol chemical composition data, water soluble, you have to put water insoluble component as well, and black carbon how much it is there, and you have to simulate the data at ambient relative humidity condition, apply in the model, aerosol optical properties model, and what it will give? It will give you something like some properties like aerosol optical depth, single scattering albedo, asymmetry factor. These are the parameters that you will get from here. But note that this model has to be first validated, all these parameters has to be validated, and this is usually validated with the real time measurements that you have. For example, in aerosol optical depth, we generally take plus minus 5% of deviation. If it is there, we assume that our chemical composition data and modeled optical properties are same. So, once you have this data, you add in the radiative transfer model, the radiative transfer model called Santa Barbara direct aerosol radiative transfer model. So, in this SB dot model, you put all the parameters along with some of the other parameters, so ozone, water vapor and surface albedo. This is very important because you have to consider different type of surfaces where you are measuring, or over the land or over the ocean. So, the parameters will be different, and when you put this one, this will give you radiative forcing values, and it will give radiative forcing at top of the atmosphere, surface and atmosphere. So, all the wavelength, all the 3 values it will give, and based on that you can not only calculate the estimate radiative forcing. So, if this radiative forcing is positive or it is negative, if it is positive means it is warming kind of things, and if it is negative then this means cooling. Okay. So, you can get these parameters, and with this parameter you can also calculate the heating rate of the atmosphere. So, that is another very important parameter, and this is how you calculate the atmospheric heating rate. You calculate delta T by T. So, heating rate in the Kelvin per day, T is time actually. So, you can put your time, usually whatever the time you are, for example, if you are putting Kelvin per day, your time has to be in the day, and G upon Cp is atmospheric lapse rate, it is constant, so it is known. G is acceleration due to the gravity. Cp is the specific heat capacity of the air at constant pressure, for example 1006 joule per kg per Kelvin. Delta Fm is the atmospheric forcing that we have already calculated. Okay, and delta P is the atmospheric pressure difference between top and bottom boundaries of the atmosphere in which most of the aerosols occur. So you have to calculate that. For example, if you are calculating for top of the atmosphere, then you have actually like atmosphere, or you have surface. Okay, so if you are calculating this one delta P, you can calculate here delta P1, or you can have a delta P2, or you can have actually like delta P3. So whatever the things that you are calculating, you can see the difference in the pressure, and then you can calculate the atmospheric heating rate. So this sums up all about the concepts of aerosol radiative forcing, forcing due to the greenhouse gases, and then concept of what you call we discussed the concept of radiative equilibrium of the earth, or the heat balance model of the earth. So this covers all the things, and now one of the very important parameter is that is there that at what, because I said that the radiative forcing calculation depends, if you remember here, it depends on the kind of SSA, single scattering albedo. Now single scattering albedo, if you remember in my previous slides, I discussed that single scattering albedo lies between 1 to 0. Of course, it is not 0. In most of the practical cases, it is somewhere around 0.3 to 0.95 or so. In some cases, you can have 0.95 or 0.90. You can have more than 0.3 is also not very typical case. So you have usually we have a variability of 0.6 to 0.95 or so in SSA. Very small scale variability we have, and but of course here this higher values means more scattering, as we discussed, because the scattering component is on the top, and lower values means absorbing ones. So there is a question that at what values the parameters can become forcing, can become cooling or negative. So this is here given surface reflectance values, and on the y-axis is actually like critical surface albedo. So if you see for different values, you can go like this, but for example here, if you see here, for example, you are having here, you can derive this constant parameters, that even if the surface albedo is very low, okay, if surface albedo is very low, surface reflectance is very low, you have very high single scattering albedo, this can be very negative. And even if you have very high single scattering albedo values here, okay, and surface reflectance very high, it can still be actually in this side, or it can be in this side. So there is a very critical value, and it's not very easy to find out that value. There is no single value of SSA on which you can say that particles will behave like scattering, or the atmosphere, there will be either atmospheric cooling or warming. So there is no critical value on that one, but there are lots of efforts going on. Okay, so this is what actually aerosol effect, and this is direct aerosol effect we talked in terms of radiative forcing, and then warming or cooling. The other things aerosols do, the presence of aerosols, they directly affect they interact with the incoming solar radiation or outgoing solar radiation, and they affect the radiative forcing of the atmosphere or the surface. The other way they can do is actually like aerosol effects, is like aerosol indirect effects, and in this one aerosols interact with the cloud, and not exactly the clouds. It could be that how the clouds is formed, or even in the cloud or within the clouds, and this happens through the physics and chemistry of the aerosol cloud interaction. This is very important. Okay, So if you have like different types of aerosols you have in the clouds, you can have, for example, natural and anthropogenic aerosols. For example, these are the small dots. They are actually like small particles here. You can have ice and liquid Cesians, like this one, ice and liquid Cesians. Then you can have grapples or hail crystals, and then you have small cloud droplets. Okay, these are the smaller cloud droplets, or you can have a larger cloud droplets. These are smaller ones, green one. Then you can have larger effects. Now what is happening here? When this radiation interacts, now you have a system. If it was a cloud only, and not only that, you have to just see this one. You have to understand two things here. That there was no, if there was no particle, this radiation could have been directly reaching to the surface. But because of the radiation, this particles either will reflect back or it will absorb the radiation, and this will keep on happening with all the particles that are there in the system. So this is actually happening a very complex phenomena or complex process that is going on. So we have to understand that one. But before we understand, let's understand the precipitation formation mechanism itself. Okay, water vapor is size somewhere around, I think, 240 nanometer or so, if I remember it correctly, and your raindrops, for precipitation to occur, the raindrop size should be 0.1 to 3 millimeter. And this means, if I just take, let's take this is a 250 nanometer for calculation, and this means this is actually 0.1 micrometer. So this means 0.1 micrometer millimeter, sorry. So this means 0.1 0.1 into 250 by into 10 to the power minus 9. This will be in the meter, and then if you put there, it will be like 10 to the power 8, and if you make it is 4, okay, and then 8, and then 10 to the power 4. So 25 into 4. So it has to particles from here to here, it has to grow by 4,000 actually. The water droplets has to grow almost 4,000 of its size in order to get precipitated, and which is not very easy process. This is, if you just consider that nucleation of the or condensation, droplets from the nucleation, formed by the nucleation. So the condensing of the water vapor on a tiny, because the relative humidity and the temperature play very important role on tiny solid particles. So the way they happens, they directly don't condense, they cannot become very big size, smaller size, and when they do, they becomes like 0.01 micron to 10 micron particles that are there. We discussed about the aerosols. So they cannot actually grow. Then they can actually, what they can do, they can either nucleate or they can condense on the pre-existing aerosol particles that are there. So once they are actually there, the droplet size increases by condensation, and once you have a particle on this one, now you have more of particle water vapor on this one, that is actually condensing, so particle size will grow, and this droplet size become heavy enough to fall, for example somewhere around 0.1 millimeter, then it can fall. But here some of these things, suppose this aerosols is actually absorbing type, what will happen? When this is actually warming, aerosol is actually absorbing, so this will trap the radiation, it will absorb the solar radiation, and this means this will become in higher energy states. When the surroundings will become cooler, what it will be? It will try to again re-radiate its energy, and when it tries to re-radiate its energy, whatever the surface condensation was there, it will be evaporated. So these many droplets, because of this evaporation, many droplets decrease in their size by evaporation, and if they, depending on the size, whether they are in this range, they will again go this process, or if they are actually sufficient enough, some of the droplets increase in the size by impact and aggregation. So together they can aggregate and they can fall as a raindrop. okay, and this is where actually like larger droplets can break up into smaller droplets also. This is also quite likely possible, but this is how the precipitation happens. Now remember, this is a very big problem here. This from here to here, there are not only the change in size is involved, but the aerosol, because this is actually condensing, they are condensing depending on this one whether it is absorbing or scattering type aerosols. And not only that, there is another very important thing, whether aerosol is hygroscopic or hydrophilic or hydrophobic. Hygroscopic means water loving and hydrophobic means water hating. So if the aerosol is hygroscopic, it can go to this process, but if the aerosols are not, they will not allow to go this process. So not only that, so aerosol types in this one is very important. This means the composition of aerosols is also becoming very important. So there are two parameters, size of the this pre-existing aerosols, and these aerosols we generally called as CCN, cloud condensation nuclei, and this size becomes very important. So size of the CCN and then becomes very and the composition becomes very important. So what happens? Lifting air cools air masses, so moisture condenses on that one, and condensation nuclei are cloud condensation nuclei are aerosols that water molecules attached to. This will be happening, and if you just talk about the typical size of CCN particles, it's around say 90 to 110 meters or so, and they could be both hygroscopic or hydrophobic as I explained, and therefore both size and chemical composition is very critical and very important knowledge of this one in order to grow the particles. The process I explained, that rising and growing, this will happen. So if you have a wind speed of 0.5 centimeter per second, sufficient to carry 10 micrometer droplets, and the critical size is somewhere around 0.1 millimeter for the precipitation to occur, and then gravity overcomes and drops fall in the end. And this is what we explained in this one. So what will happen now? Consider a situation. You have a cloud system in here, you have water vapor that is there here, and you have aerosols in this one. What will happen? Whatever the incoming solar radiation is there, they will be reflected back, okay, and the part of this one will be transmitted to this one. Now, if you have a smaller number of particles here, we will explain this one very clearly. If you have a smaller number of particles, so for given liquid water content, N is smaller, okay. So liquid water content per particles will be higher, okay. But if you somehow increase, what will be the liquid water content? If N is increased, then what will happen? Liquid water content to N ratio will be lower. This means there are less likely chance that the particle can grow. So this is not on land. So this means here you will have actually more CCN, more cloud. Although you have more CCN, but these CCNs are smaller in size, they will not be actually more cloud droplet will be formed, but these droplet will be very small. So they will not be, they will be stronger cloud albedo. So the albedo will increase in this case, more will be reflection. But at the same times, this more, although you have more CCN, these CCNs will not be converted into droplets, and they will not be converted into droplets. So this precipitation cannot happen here. While in this case, this is what is actually aerosols indirect effect we call it, okay. So this is what is explained here. The larger the number of CCN, the higher is the resulting cloud albedo, okay. If you increase the number of particles, the reflection will be more. So this will be actually more albedo. This is called first indirect effect, and higher reflectivity. This means this will be actually having a cooling effect, and this effect is also called as Tommy effect, okay. He discovered for that time. So this means if you increase anthropogenic aerosols, there will be an increase in the CCN in the given size, say 90 to 110 nanometer particles will increase with the smaller radius, droplet size. This means an increase in effective radius, okay, if you increase the radius, there will be a decrease in the cloud reflectivity, and if you increase the number of the particles, if you decrease the size, effective radius, that cloud albedo will increase. This is what is actually important, I explained here. And in this case, what will be happening? This will be a lower precipitation, and efficiency, this is also called as solar second indirect effect. Okay, this is actually called first indirect effects, that larger number of CCN results in the smaller resulting in high cloud albedo. This is actually first, and then resulting in a lower precipitation. This is called second indirect effects or cloud lifetime effects. In this case, what will happen? Because the precipitation will not increase, precipitation will not be there, so this cloud lifetime will increase. So this is another very important thing. So yeah, with this one, I think I stop here, and I will. The last lectures will be there on the aerosol cloud feedback mechanisms, and then once we complete this one. So thank you very much.